Hello, everybody, and welcome back to another lecture in Geography 340, Climatology. I'm Dr. Zach Hilgendorf. Today, we're going to be talking about atmospheric moisture patterns. Really starting to. So a quick aside, the amazing water molecule. Here it is in all of its glory. We see these two molecules bonded by a hydrogen bond. So water is a chemical compound. It's dipolar. Each atom has a dipole or partial charge. It is made of two hydrogen atoms and one oxygen atom, pretty obvious, H2O. And it is formed by polar covalent bonds between atoms, which are highly stable. It's one of the more stable molecules. And then the hydrogen bonds between molecules. And a good friend and colleague, Dr. Gary Running, would often show this in his Geography 104 lectures. Flip it upside down, it looks like Mickey Mouse. So we're looking at water phases and phase changes. So water phase is determined by the degree of hydrogen bonding. We look at here, we got individual molecules kind of in our gaseous form, clusters of molecules in our liquid form, and a rigid framework of molecules in our solid form, gas, liquid, water, and ice. We're breaking these hydrogen bonds through sublimation, vaporization or evaporation, and melting. Water molecules absorb energy through a cooling process. We're forming hydrogen bonds during deposition, condensation, and freezing. Water molecules release energy. These are warming processes. So talk about humidity. So humidity is basically the water vapor content of air. So what is the average water vapor content of air? What are sources of humidity and what are sinks of humidity? Well, those are all good questions I think we're probably going to answer here. We see evaporation from large bodies of water or superficial bodies of water in general, that direct connection between the water and atmosphere. We see transpiration prevalent through kind of the respiration of plant matter. And both of these evapotranspiration processes add water vapor to our atmosphere through once it reaches the atmosphere, we have condensation or deposition of that water. So how do we look at humidity indices or measures? We talk about specific humidity, so the mass of water vapor per unit mass of air. We usually look at that in grams per kilogram. We talk about mixing ratios. So the mass of water vapor per unit mass of dry air, and again, grams per kilogram. So specific humidity, if specific humidity was to equal 10 grams per kilogram, the mixing ratio would be 10 grams per 0.99 kilograms. That would equal 10.10 grams per kilogram. If the specific humidity was 20 grams per kilogram, mixing ratio would equal 20 grams divided by 0.98 kilograms. That would equal 20.41 grams per kilogram. Our 30 grams per kilogram, that would give us 20 grams divided by 0.97 kilograms, or 30.93 grams per kilogram. That's our mixing ratios. We talk about vapor pressure. So the part of air pressure due to water vapor. Air pressure is the force per unit area exerted by randomly moving gas molecules bouncing off of a surface, which we can see here. And it is a partial pressure of water vapor in millibars. We talk about relative humidity. So it's the ratio of actual water vapor content of air to what the water vapor content would be if the air were saturated. That word saturation, or saturated air, is a humidity state that exists when the rate of evaporation from and the rate of condensation onto a flat water surface are equal. So basically, we're looking at a parcel of air that is fully saturated when the rate of evaporation and the rate of condensation onto a flat water surface are equal, or 100%. You can see here, this little diagram, if our bowl of water here on this table that is enclosed by, we'll say, like a perfectly formed and encapsulated glass shell, we open it, those molecules will begin evaporating and filling this glass shell. That'll increase the pressure within that glass shell. Until a point where we are at an equal or 100% saturation, which will increase over time. So saturation vapor pressure here is equal to 12.3 millibars. At 20 degrees Celsius, it's actually equal to 23.4 millibars. So if we look at this graph here, saturation vapor pressure versus temperature, kind of see this nice increasing curve from negative 20 degrees Celsius through 40 degrees Celsius mapped here. Now, if we look in this portion, it's not perfect. This is super cooled water, so we see a bit of a deviation from the expected trend. So there is ice. So the saturation vapor pressure at about negative 10 degrees Celsius, about 2.9 millibars. For super cooled water, for ice, it's about 2.6 millibars. So if we look here, what is the relative humidity of this air when our temperature is equal to 30 degrees Celsius and our vapor pressure is equal to 30 millibars? So relative humidity is going to equal vapor pressure divided by saturation vapor pressure. Percent relative humidity is equal to vapor pressure divided by saturation vapor pressure times 100, just to get a percentage. So at 30 degrees, we are here at about 42, give or take. So 42.5 millibars is our saturation vapor pressure. So 30, which is the vapor pressure that we have recorded, divided by 42.5 gives us about a relative humidity of 70.6%. Okay, how about this? We have temperature is 25 degrees Celsius, and our vapor pressure remains constant at 30 millibars. Here we're at about 31.7 millibars for our saturation vapor pressure. And we are at 30 millibars, again, for our vapor pressure. That gives us 94.6% relative humidity. So this gets at the concept of kind of dew point here. So that is the temperature at which air, given its vapor pressure, would be saturated. So if we look back here again, let's figure out what the dew point of this air, rather than the relative humidity, would be. Temperature is equal to 30 degrees Celsius. Vapor pressure is 30 millibars again. So at 30 millibars, our dew point is going to be about 24 degrees Celsius. Now, if it was temperature was 25 and our vapor pressure was 30, it's still going to be 24 degrees Celsius. That dew point doesn't fluctuate with air temperature, it fluctuates with vapor pressure. All right, so what is the vapor pressure of air where our temperature is 25 degrees Celsius, our dew point is 15 degrees Celsius? Well, simply we're using the dew point that gives us a vapor pressure of 17 millibars. We can see where that is looking at our air temperature. So what's the relative humidity or percentage relative humidity of this air? Well, if we look at our air temperature and we go across, we can see our saturation vapor pressure is 31.7 millibars. If you do the math on that, it gives us 0.536 or 53.6% relative humidity. And then what's the vapor pressure of this air where temperature is 20 degrees Celsius and dew point is 15? Well, our dew point hasn't changed. So that is still 17 millibars as our vapor pressure. Our air temperature has changed. So what's the relative humidity percent or percent relative humidity of this air? Looking at our air temperature, that gives us 23.4 millibars. So we get 72.6% relative humidity. And here we can just look at the two graphs that we kind of use to determine saturation specific humidity versus temperature and saturation mixing ratio versus temperature. So we can look at this graph here. This is a graph of air temperature at the Eau Claire Regional Airport from September 29th of 2012, going from midnight to midnight of that day in degrees Celsius. So we can see just after sunset, we see that rapid rise in air temperature as the solar insolation is heating the surface and heating these lower parcels of air. Now we can see our dew point. It doesn't fluctuate nearly as drastically as our air temperature does. We can kind of see a relatively flat dew point throughout most of the day here. And based on the rapid fluctuation and increase in surface air temperature and the relatively stable dew point, we can see how relative humidity changes throughout the day. So that's that green line there, where we see a rapid decrease through the peak of surface air temperature for the day as it slowly increases as the sun sets and our temperatures decrease and the earth and surface is losing that heat in the form of long wave radiation. And here we can see kind of an example of dew point climatology within our conterminous or the lower contiguous United States. So in average July dew points, we see sub-zero dew points throughout much of the west. So very dry air, as we're thinking of it, throughout much of the western portion of the United States versus higher dew points along the Gulf Coast and kind of increasing latitudinally throughout much of the eastern portion of the US. In January, we see very cold dew points throughout nearly all of the United States. That varies with deviations in latitude, with a few changes that are driven by local climatological or topographic shifts. So that's all for this video. And in the next one, we're going to start jumping into clouds and precipitation, but that is all for part 2. We'll have our exam shortly, but this is all the material that is covered in part 2 of the course. So I hope this all made sense. Please feel free to reach out with any questions, and I will see you in the next video. Thanks.